Hi, everyone. Welcome back to section 5.2. We were looking at different ways to find a binomial probability distribution. And we saw some examples where we have a probability distribution where we know exactly how many number of successes we will have. For example, in this method where the x value was equal to 3, which is the number of successes. But in example 2, we were looking at the results of 252 wins. So we have to do up to the 251 losses. So it's 1 minus the probability. So assuming that wins and losses are equally likely, we saw that P and Q were equal. Now we let X be equal to 251. We're going to be using our calculator, our TI-80 384, but instead of doing a binomial PDF, we're going to be doing a cumulative binomial distribution that looks like Binos MCDF. And I projected how to use that in calculate 84, which was second vars. Now, where we saw the third method was not using the formula, not using your calculator, was looking at the table A-1. You can find that in Appendix A. For us, we're typically not going to be using the table. We're not going to do that. However, I do want to show you an example on how to use the table in case. So devil of a problem. Based on a Harris poll, 60% of adults believe in the devil, assuming that we're randomly selecting 5 adults. Use table A-1 to find the following. Find the probability that exactly 3 of the 5 adults believe in the devil. Well, first of all, how do we know that this is indeed a binomial probability? Well, we have the probability that two options. So you either believe or not believe in the devil. In the devil. Okay. So that gives us 2 options, successes and failures. We know that exactly 3. So the number of successes is 3. We have a probability that's 0.6. And the number of the number of trials in this case would be 5. And we would be able to find the probability. Now, what is the probability that the number of adults who believe in the devil is at least 2? So it would be at least 2. That would be 2 or more. At least 2 people. So that would mean the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5. So you would have to do it multiple times. Or if it's saying at least 2, you would do 1 minus the probability of 0 plus the probability of 1. The probability that no one believes in the devil, and the probability that 1 believes in the devil, because 2 or more will believe in the devil. So what we can do is we can create a probability distribution, and we can use our calculator for this. But then for this, we can say, okay, well, we can do a distribution where we can subtract at least 1. So what we're going to do is we're going to look at the table I-1. The number of n is 5. And when we're looking at a binomial probability, here they are. So what happens when the probability is 0, the probability is 1, the probability is 2, and so on. So then what we're going to do is we're going to look at the table here. Probability when x is equal to 0, the probability when x equals 1. Well, we can take these 2 numbers, right? The first one was easy because the number of successes when P is 3 is 0.346 by just looking at the table. So by looking at the table, if I wanted to find, well, what's P of 4, the probability of being 4 would be 0.259 of those believing in the double. But now I want to find, okay, well, what's the probability of at least 2? So I'm going to do 1 minus the probability of those that don't believe in 0.01 plus 0.077. Those are the probability that at least 2. So then if I add these numbers, 0.01 plus 0.077, I'm going to do 1 minus 0.087. So I'm going to do 1 minus, using my calculator, 0.087. That gives me 0.913. That means that the probability of the number of adults who believe in the devil is at least 2 is 0.913. Or you could have done the probability of 2, probability of 3, 4, or 5. So you would do P2, P3, P4, P5, which is exactly what I had over here. So there's 2 ways of calculating it. 1 minus P0 plus P1, or P2, P3, P4, P5. You get the same answer. And there we have it. Now, when we're finding the mean, the standard deviation for a binomial distribution, your mean is going to be a population. Remember, it's a parameter. So for a binomial distribution, we'll have a population mean to be the number of trials times your probability. Your standard deviation would be the square root of n times p times q. And the variance would be, remember that the variance is the standard deviation squared. Okay, that's the variance. So that's n times p times q, and the standard deviation, well, we just take the square root of that. Now we have the range rule of thumb that says significantly low values are values less than or equal to mu minus 2 times the standard deviation. High values would be a value greater than or equal to mean plus 2 times the standard deviation. And there's no significant values when you are between. So for example, here we have mu minus 2 sigma. So here we have mu, the mean. We have the mean minus 2 sigma, mu plus 2 sigma. So over here, these are significantly high. And then over here, we have significantly low values. Oops, let me change that to a yellow. This would be significantly high. And then here, the ones in the middle, the green, don't have significance. So that's the range rule of thumb for finding the binomial distributions. Okay. Now let's look at an example using parameters to determine significance. So a previous example involved n to be 460 overtime wins in NFL football games. There's our probability, there's Q. By assuming that winning overtime does not provide an advantage, so both teams have the same chance. They're telling us already, they want us to find the mean and the standard deviation wins for 460 games. Well, remember, to find the mean, it's n times p. In this case, is 460 times 0.5. So let's punch that in our calculator. 460 times 0.5, 230. So the mean is 230. The standard deviation is going to be, remember, it's going to be the square root of n times p times q. which is the square root of 460 times 0.5 times 0.5. Let's plug that in our calculator. So we want the square root of 460 times 0.5 times 0.5 and close it. And that's going to give me 10.723. So then I want to know, using the range rule of thumb, to find the values separating the numbers of ones that are significantly low and significantly high. Well, if I want to find significantly low, I need to do the mean minus 2 times the standard deviation. So that's 230 minus 2 times 10.723. That's going to be my significantly low value. So let's plug that in. So it's 230 minus 2 times 10.7723. And that's going to be 208.55. And then I want to know, okay, well, what's going to be my significantly high? It's going to be mu plus 2 times the standard deviation. So that's 230 plus 2 times 10.723. So let's find what that is. So 230 plus, that's going to be 251.44. So now that's my significantly high. Significantly high, there it is. Significantly low, it was 208. And there's our mean, my population mean. So that means that letter C is a result of 250 significantly high. And the answer is yes, because if you put it on the scale, our mean was 230. Our significantly low number was 208.55. My significantly high was 251.44. And 252 is actually over here. So 252 is significantly high. So yes. Okay. There it is. Let's plug it in. Let's check. There it is. So yes, it is significantly high because it's greater than our significantly high boundary. Okay. Now, using probabilities to determine when the results are significantly high or significantly low, we use the same properties that we've been using. The probability of X or more, it's less than or equal to 0.05. The probability of X being less than, it's less than or equal to 0.05. So this is using probabilities to determine when results are significantly high or significantly low. But we've been using the past formula to actually determine the actual values. Okay, so what's the rationale behind the binomial probability formula? Well, remember that this is actually just this part, this highlighted green area. This is a combination. This is the beginning of NCR. N factorial over N minus R factorial, R factorial. This is our combination. And then we have the number of outcomes with exactly X successes among N trials. And then the second part is the probability of X among N trials for any particular order. So it's kind of divided by two parts. The first one is the number of successes and the other is the probability. And that ends with section 5.2. Let's go over 5.3, Poisson's probability distribution. Poisson's probability distribution is another category of a discrete probability distribution. Remember, discrete is something that's countable. something that is countable or finite, something that will end eventually. The Poisson probability distribution is a discrete probability distribution. The only difference is that it applies to occurrences of some event over a specific interval. That's the difference between a probability distribution and Poisson's probability distribution. Poisson's is very specific over an interval. So the random variable x is the number of occurrences of the event in an interval. The interval can be time, distance, area, volume, or some similar unit. So these are the types that we can see. Poisson's probability distribution is given by this following formula. The probability of x is the mean, the population mean raised to the x times e to the negative mu, which is the population mean, divided by x factorial. E is a transcendental number. E is a number that is defined by many, there's more decimals to it. 2.71828. And then mu is the mean of numbers of occurrences in the event in the interval. So the population mean in this case would be in an event that occurs in an interval. So what we're going to be using is that following formula. What are the requirements for Poisson's probability distribution? Remember, each of the three sections that we worked for, probability distribution, a binomial distribution, and Poisson's all have requirements. One of the requirements for Poisson's probability distribution is the random variable x is the number of occurrences in some interval. Again, we see that word like 3 times now. The occurrences must be random. The occurrence must have independent of each other, and the occurrences must have a uniform distribution over a interval being used. So when it's uniformly distributed, remember they're mostly the same. A uniform distribution is that the probability are mostly the same. What are the parameters? What are we going to be using? We're going to use the mean, mu. The standard deviation is going to be found by taking the square root of the mu or the population mean. The properties of Poisson's distribution is a particular Poisson distribution is determined only by the mean. So the mean is the most important. Is the most important variable, if you will, in the formula for Poisson, of course. A Poisson distribution has possible x values 0, 1, 2 with no upper limit. So you don't have an upper limit for x. Okay, so x are the possible values of the value. So what we're going to do is we're going to do an example. For the 55th year period since 1960, there were about 336 Atlantic hurricanes. Assume that there exists a Poisson's distribution. We want to find the mean number of hurricanes per year. Alrighty, so to do that, we want to find, okay, well, how many hurricanes happen for per year? So the mean, it happened through a period of time. For a 55-year period since 1960, there were 336. So there's the amount of years. And there was how many. So what we're going to do is we're going to be creating the number. We're going to find the mean. The Poisson distribution applies because we're dealing with an occurrence as an event over a period of a time of a year. The mean number per hurricanes is the number of hurricanes divided by the number of years. So we know that there was 336 over a period of 55 years. So then the mean is 6.1 hurricanes per year. Okay. Now the next part is asking us to find the probability that a randomly selected year there were exactly 8 hurricanes. Find P of 8, where P of X is the probability of X. Atlantic hurricanes in a year. So what we're going to do is we're going to actually plug it in into the formula. So we want to find P of 8, which is, well, the mu is 6.1, our x is 8. So what we're going to do is we're going to say, okay, well, that's 6.1 raised to the 8th times e to the negative 6.1 all over 8 factorial. So another way you can do this is by using your calculator. So let me open it up. There's calculate 84. I'm going to clear it. And I'm going to use my parentheses. So it's going to be 6.1 raised to the close parentheses, open parentheses 8, close it. And then I'm going to do times. So let me close that one, times, open parentheses, e raised to the open parentheses, negative 6.1, close parentheses, and then close the parentheses again. And then I'm going to take the whole thing, put a bracket, and then I'm going to put a division next to the bracket, open another bracket to say what I'm going to divide it by. And I'm going to divide it by 8, and then I'm going to put an exclamation, and I'm going to hit enter. And that's going to give me 0.10664. So the probability so part B, when I plug it in, I'm going to get 0.107 from part B. There it is. I plugged it in, and that's the answer I got from my calculator. Now, part C is saying, in this 55-year period, there were actually 5 years with 8 Atlantic hurricanes. How does this actual result compare to the probability found in part B? So actually, it was 5 and 8. So what can we say about this? Well, it's saying once we find the probability of 8 from part B is the likelihood of getting 8 Atlantics in 1 year in 55 years. So if we take 55 times 0.017, the actual probability I get 5.9. 5.9 is actually relatively close to 8. That means that Position has it works well. I mean, it does give it an approximation, not the best, but it is a model that can work well. So for us, once we find the probability of 8 within 8-year hurricanes, we got 5.9. So 5.9 is reasonably close to 8. Now to look at more detail for Position's distribution as an approximation to a binomial. The Position is sometimes used to approximate the binomial distribution when n is large and p is small. One rule of thumb is to use such an approximation when the 2 following requirements are both satisfied. So we can kind of mimic the Position to approximate a binomial. This is only when n is large and the probability is small. So we have to say that n has to be strictly greater than 100, and the probability of n times p should be less than or equal to 10. And these are the 2 conditions that have to be met in order for us to use Position as an approximator. So if both requirements are satisfied, there's a formula to find the mu, n times p. Okay, so this is what we're going to use for an approximation. So let's try and let's look at an example. Main pick 4. In the main pick 4 game, you pay 50 cents to select a sequence of 4 digits from 0 to 9, such as 1,377. If you play this game once every day, find the probability of winning at least once in a year with 365 days. So first of all, we have to find the probability, and we find n. So we need to find n first. So we know n. And this is, of course, a Position because it's an interval. We're looking at an interval in a day. We know that n is 365, And from the probability, there is one set of winning. How did I get that? Well, they're saying you're going to pick 4 digits from 0 to 9. Remember when we were looking at 4 digits, what is the probability for that? And we saw that back in chapter 4 on counting, when we were looking for counting, when we were looking at probabilities, 1 chance, 2, 3, 4. From 0 to 9, I have 10 options, 10 options, 10 options, and 10 options. So that's 10 out of 4. That's 1 out of 10,000 options. That's my probability. That would be selecting the correct one, selecting the winning one. So our probability is, so the probability is 1 out of 10,000. So then we can say that n is greater than 100 and n times p is going to be less than or equal to 100, less than or equal to 10. So let's test that. So we find the mean, n times p, 365 times 1 over 10,000, we get 0.0365. And we know that n times p, if we multiply, we know that n is greater than or equal to 100, and n times p is equal to 0.03, which is less than or equal to 10. So both conditions are satisfied. And all we have to do is substitute our mu and our x into the value. Well, because we're looking at having found that the value of mu, we can proceed for finding the probability for exactly x. So we want to find, the strategy is, what's the probability of being 0? That means no wins in 365, because that's at least 1. So we're going to do is 1 minus that probability. Remember, there was 2 ways of finding this. 1, 2, 3. I'm not going to do all 364, right? I'm just going to do 1 minus the probability of the 0, because we're going to be using the complement here, because it's saying at least 1. So at least 1, that would be 0. So first we need to find the probability of p being 0, the no wins. So the probability of at least 1 is 1 minus the probability that we find. So when we plug in x being 0, remember 0 factorial is equal to 1. When we place this in our calculator, we're going to get 0.9642. But this is not our answer. This is the probability of not winning. This is the probability of not winning. The probability of not winning. No wins in 365 days. So that would be the probability of not winning. But if we want the probability of winning, we have to do 1 minus the probability of not wins. Remember, it's 1 minus the complement. That's going to give us 0.0358. So again, it's very small. So the probability of winning at least once in a year is 0.03, which is very unlikely. So again, the Poisson distribution works very well here. So we actually compare the value 0.0358 and the value of the mean. So the mean and your actual value will be very close. So Poisson gives us a very nice approximation. It works quite well. And with that, we finish section 5.3, Poisson's distribution. Okay. So in chapter 3, we saw probability distribution. We saw binomial probability distribution in 2 ways. They were both discrete. We saw that we could have done a formula. We could have used the table A-1, and then of course, we could use our calculator where we have successes and failures. We have a cumulative binomial distribution, and we have the exact amount. And then for Poisson session 5.3, it had to occur in an interval amount of time. It occurs in a sequence amount of time in an interval. We were able to find the mean, which was the most important variable for our formula for Poisson. And in this case, we know that if n is large enough and our probability is small, we can actually use Poisson distribution to approximate a binomial. But again, that's only if n is greater than or equal to 100 and n times p is less than or equal to 10. All right, and that is the end of section 5.3. Thank you, and I'll see you guys next time. Bye-bye.